Right now, as you listen to this, something is pressing on every atom of your body. You call it gravity, and you have been told all your life that it is a simple pull downward. Drop a phone and it falls. Let go of a mug and it falls. Planets circle stars because of the same invisible tug. It feels obvious, almost boring. Yet the modern view of the universe quietly says this story is wrong in a very deep way. You are not being pulled down at all. If that sounds wild and you want to keep digging into how reality actually works, tap like and subscribe so we can explore it together. Let us start with the story you already know. You hold something in your hand, open your fingers, and it falls toward the ground. You stand on Earth and feel weight pressing into your feet. You look at images of the solar system and see Earth looping around the sun because the sun pulls on it. That basic idea works well enough for daily life. It is simple, it is teachable, and it gives answers that are close enough when you are only building bridges or throwing baseballs. It is like looking at the horizon and deciding Earth must be flat because it looks flat from where you stand. Useful in a narrow way, but dangerously incomplete. To see why that matters, we walk back to the late 1700s in your mental time machine. Before Isaac Newton, people had many ideas about why things fall and why planets move, but most of them were guesswork or philosophy. Newton did something different. He turned gravity into math. He wrote down a rule that said every mass in the universe attracts every other mass. The strength of that attraction grows with mass and weakens with distance in a very specific way. Double the distance and the pull drops to a quarter. Triple the distance and the pull drops to a ninth. One simple pattern, stretching from apples to the moon. The power of that rule was ridiculous. It explained the rhythm of tides, as the moon pulls different parts of the oceans by slightly different amounts. It explained why the outer planets creep along their orbits more slowly than the inner ones. Astronomers even used Newton's equations to find an entirely new planet. Uranus was drifting slightly off track, so they calculated where an unseen mass would have to be to cause that wobble. They pointed their telescopes, and there it was, Neptune, almost exactly where the math said it should be. For 2 centuries, gravity as a force seemed untouchable. Yet even inside this triumph, something strange was hiding. Gravity is unbelievably weak compared to other forces of nature. A tiny kitchen magnet can pick up a paperclip off a table. That magnet is fighting the gravitational pull of the entire planet and winning easily. 2 people standing side by side attract one another gravitationally with a force so small that it is less than the weight of a single bacterium. On the scale of atoms and molecules, electromagnetism completely dominates. So why does this weakling of a force end up shaping galaxies, sculpting the solar system, and holding atmospheres in place? That imbalance is one of the quiet mysteries behind gravity. The other crack was even subtler. Mercury, the planet closest to the Sun, follows an oval orbit that slowly rotates over time. Newton's gravity predicts how fast that oval should turn because of the tugs from all the other planets. When astronomers did the sums, they got an answer that was just a little bit wrong. Mercury was turning about 43 arcseconds more each century than Newton's theory allowed. That is less than a tiny fraction of a degree. Barely anything, but real and measured. People tried patching the equations. They invented an unseen inner planet. Nothing worked. A tiny mismatch at the edge of the solar system was quietly telling us that the idea of gravity as a simple force might not be the final story. Enter Albert Einstein with a completely different way of thinking. Instead of asking what invisible thing pulls on what, he asked a more radical question. What if space and time themselves are not rigid and separate? What if they are one flexible fabric, called spacetime, that can be bent and warped? In this picture, you do not sit in a fixed arena while forces shove you around. You and every object are moving along natural paths in a 4-dimensional landscape that responds to matter and energy. Mass does not summon a force. Mass reshapes the geometry and tells space-time how to curve. That sounds abstract until you translate it into motion. On the curved surface of Earth, the shortest path between 2 distant cities is not the straight line drawn on a flat map, but a great circle route that looks curved on the page. In the same way, in curved spacetime, the natural paths of objects look curved when you project them into your three-dimensional view. Planets are not being yanked around by an invisible hand. They are following the straightest possible tracks through the warped geometry created by the Sunday. This reframe leads to one of the most unsettling ideas in the whole story. When you are in freefall, you are not feeling gravity at all. You are doing what the universe wants you to do, gliding along a natural path in space-time. When you stand on the ground, your body is trying to follow that path toward Earth's center, but the ground pushes back with electromagnetic forces in the atoms of the floor. That push is what you feel as weight. In other words, the abnormal state is standing still. The natural state is falling. Gravity as a force disappears, and what remains is geometry resisting your attempt to stay put. In this documentary, we are going to follow that thread all the way out. From this odd feeling in your feet, to time running at different rates on mountains and satellites, to light bending around massive objects, to black holes where curvature becomes so extreme that time and space almost trade roles, to ripples in space-time from colliding stars, and finally to a universe filled mostly with invisible forms of matter and energy that we only know through how they curve space-time. By the end, gravity will look far less like a simple pull, and far more like a deep story about the shape of reality itself and your place inside it. Before we bend space-time, we have to appreciate just how good the old picture was. For most of human history, the heavens and earth were two different realms. Apples fell for one set of reasons. Planets wandered across the night sky for some completely different, mysterious cause. Philosophers argued, but nobody could make the numbers line up. Then along came Isaac Newton, sitting under his famous apple tree in your mental cartoon, and did something much more radical than ducking a falling fruit. He wrote down a set of rules that treated the falling apple and the orbiting moon as the same event playing out on different scales. Newton's key idea is surprisingly simple to say. Every chunk of matter in the universe attracts every other chunk. Your body pulls on Earth. Earth pulls on you. The sun pulls on Earth, and Earth tugs back on the Sunday. The strength of that attraction depends on how massive the two objects are and how far apart they are. Double the mass and the pull doubles. Double the distance and the pull does not just halve, it drops to 1/4. This pattern, where the strength fades with the square of the distance, is called an inverse square law, and it shows up all over physics. You can feel the consequences of this law every time you stand up. So the attraction between you and the planet is strong enough to press your feet into the floor. You and a pencil on the other side of the room also attract each other, but that pull is so tiny you will never feel it. Two people standing a meter apart pull on each other with a force smaller than the weight of a single bacterium, which is why a weak fridge magnet can yank a metal spoon upward against the pull of the entire planet and win without even trying. This is a clue to something very deep. Gravity is incredibly weak compared to the electromagnetic force that holds atoms together and makes magnets work. On everyday scales, gravity loses by around 39 orders of magnitude. That means if you could somehow build a gravitational wave detector so sensitive that it reacted to a single person walking past, its two arms would have to be about as far apart as the distance from our sun to Saturn, roughly 10 billion kilometers. Anything smaller and random jitters at the atomic level and thermal vibrations drown out the signal. We do not live in that kind of lab. The friends that are liking are, that's one maybe this really oppressed. So you never notice the tiny gravitational games happening between you and your chair. If gravity is that feeble, why does it rule the universe on large scales? Because electromagnetism has a habit of canceling itself out. Positive and negative charges attract and neutralize. On the scale of planets and stars, almost everything is electrically neutral. So electromagnetic forces mostly balance. Gravity never cancels. It is always attractive, always pulling more mass into clumps that then pull in even more mass. Weak in small doses, unstoppable when you let it pile up for billions of years. Newton's equations did more than explain falling objects. They turned the solar system into a predictable machine. Johannes Kepler had already described the shapes of planetary orbits from observation, saying they were ellipses rather than perfect circles, and that planets speed up when nearer the sun and slow down when farther away. Newton showed why. His law of gravitation, combined with his new laws of motion, produced Kepler's rules as a natural consequence. Suddenly, the clockwork of the heavens and the motions on Earth were different chapters of the same equation. The true flex of this theory came in the 19th century with a planet that did not yet exist on any map. Astronomers had been tracking Uranus and noticed that its orbit wobbled just a little bit compared with what Newton's laws predicted. Not much, just a subtle deviation. Two mathematicians, Urbain Le Verrier in France and John Couch Adams in England, approached the puzzle in the same way. If Uranus was misbehaving, perhaps something else was tugging on it. Something massive but unseen. They ran the numbers backward, asking what kind of invisible planet, in what location, would produce exactly the observed deviations. Armed with those predictions, astronomers pointed their telescopes to the patch of sky that the math indicated. Practically at once, they found a new planet, Neptune, hanging almost exactly where the calculations said it should be. This was not a lucky guess. It was a demonstration that Newton's invisible force was real enough for you to discover a world you had never seen just from its gravitational fingerprints on another planet. For scientists of that era, this felt like the final word. Gravity, as Newton had written, it seemed to be the law behind the clockwork. For more than 200 years, nobody could seriously challenge this view. Newton's gravity steered artillery, guided sailing ships, predicted eclipses, and nailed the return of comets to the sky with uncanny accuracy. Engineers built bridges and railways under the assumption that space and time were fixed stages, and gravity was a force acting within that stage. The idea that something this successful could be fundamentally incomplete would have sounded almost insulting. And yet, as always in science, the universe kept a few awkward details in reserve. One of those details was Mercury. Because it is so close to the Sun, Mercury orbits on a tight, fast ellipse. That ellipse is not fixed in space. It slowly rotates, a motion called precession. Newtonian gravity predicts how much precession you should get from the combined pulls of all the other planets. When astronomers measured Mercury carefully, they found that its orbit was twisting about 43 arcseconds more per century than Newton's theory allowed. That is roughly 1/8 of a degree in 100 years. A tiny mismatch, but too big to ignore when your theory is supposed to be exact. Scientists tried everything to patch the discrepancy without touching Newton. Maybe there was another hidden planet even closer to the Sun, which they called Vulcan. Maybe some ring of dust was tugging on Mercury. Observers searched during solar eclipses for faint dots near the sundial. They recalculated orbital tables and tried slightly tweaked versions of the gravitational law. Nothing worked. Vulcan refused to appear. The numbers refused to budge. This is where the drama starts to build. On the surface, nothing seemed wrong. Newton's equations still gave the right answers for almost everything anyone cared about. But that stubborn extra twist in Mercury's orbit was like a hairline crack in the foundation of a building. You can ignore it for a while. You can patch the paint. Yet the structure is no longer perfect. There is a question hanging there that will not go away. That question, combined with deeper puzzles about the nature of time and motion, primed physics for a revolution. A young patent clerk named Albert Einstein would eventually step into that crack and widen it into an entirely new view of reality. He would keep the practical successes of Newton while quietly replacing the underlying story. Gravity would stop being a force reaching across space and become the way space and time themselves bend and curve. But to understand how he pulled that off, we first have to merge space and time into a single thing. That is where we go next. To really break gravity free from the idea of a pull, we have to do something that feels almost illegal. We have to mess with time, not just with clocks and schedules, but with the thing you feel flowing as your life moves forward. For most of your experience, space is where things are, and time is when they happen. they feel like different categories. You can walk north and south as much as you like, but time only marches forward. You never confuse a minute with a meter. So how could these two be parts of the same thing? Start with space on its own. You already have three directions to move in: forward and backward, left and right, up and down. If you live in a city, that is how you mentally navigate your daily life. Add one step forward, turn right, climb the stairs. Each of those moves can be measured with a ruler. Now layer time on top. You meet a friend at a certain place at a certain time. That meeting is only fully defined when you know both the where and the when. For a long time, physicists treated time as absolute. The same for everyone, everywhere. If a lightning bolt struck a tree at a certain moment, that was a single universal now. You and someone on the other side of the planet might disagree about how bright it looked, but not about when it happened. Then Einstein took apart that comfortable idea with the same ruthless logic he later aimed at gravity. Imagine two flashes of light at opposite ends of a moving train. A passenger in the middle of the train, who is moving toward one flash and away from the other, will not. For them, the light from the front reaches them after the light from the back. Both are using the same laws of physics, and both are right in their own frames of reference. The question of whether the two flashes were truly simultaneous has no single answer. Once you accept that, time stops being a rigid backdrop. The exact way you slice the world into now, before, and after depends on how you are moving. Distance and duration mix together. The speed of light stays fixed, and to make room for that rule, the universe lets time and space stretch and squeeze. Fast-moving clocks tick more slowly. It is how reality preserves one simple rule, that light in a vacuum always travels at the same speed. At this point, treating space and time as separate starts to look clumsy, so physicists do something smarter. They merge them into space-time. Think of every event in your life as a dot in a four-dimensional map. 3 coordinates for where it happened, 1 for when. Your whole existence traces out a long thread in this map, called a world line. You wake up here at this time, travel there at that time, and so on. Planets, photons, and galaxies each have their own world lines, snaking through the same four-dimensional fabric. So far, we have only been talking about flat space-time, where no gravity is involved. You can still have weird effects, like time dilation and length contraction, but the underlying geometry is simple. Straight lines stay straight. The shortest path between two events is a kind of straight world line. In this calm, force-free world, an object that is not being pushed or pulled just cruises along that straightest possible path at a constant speed. That is the heart of what physicists call inertia. Now here comes the move that transforms gravity. Einstein realized that free fall, the kind of motion you have when you are dropping with nothing pushing on you, looks locally identical to floating far away from any masses. Imagine being inside a closed elevator. If the elevator is drifting gently in deep space, you and everything around you float. If someone turns on a rocket that accelerates the elevator upward, you feel pressed to the floor. No window, no stars, just the interior of the cabin. You would say you feel gravity. Now consider that same elevator near Earth. If the cable is intact, the floor presses on your feet, and you call that weight. If the cable snaps and the elevator falls, you and the elevator accelerate together. For a brief time, you float. Let go of a ball, and it hovers next to you because you are both falling along the same path. Again, no windows. Again, you only have the cabin to look at. Now, you would say there is no gravity. Floating in deep space and falling freely near Earth feel the same. This is the equivalence principle. Locally, in a small enough region of space-time, you cannot tell the difference between being weightless in freefall and cruising in gravity-free space. Likewise, you cannot tell the difference between standing on the ground in a gravitational field and standing in a rocket that is accelerating in empty space. Your instruments, your inner ear, the strain in your muscles, all report the same thing. Something is pushing the floor up into you at one Earth gravity. Once you commit to that principle, gravity stops looking special. It starts to look like a side effect of how you are moving through space-time. Free fall becomes the default motion. Weight becomes what you feel when something forces you away from your natural path. The everyday idea that you are at rest when you stand on the ground and in motion when you fall gets flipped. On the level of space-time geometry, falling without resistance is the purest expression of doing nothing. So what does this have to do with curvature? Picture the surface of Earth again. Draw the shortest path between two cities on a globe. It is a curve called a great circle. If you lived your entire life on that surface and never saw the whole planet from space, you might insist that you were walking straight. Your neighborhood feels flat. Only when you zoom out do you notice that what felt like straight lines are actually curves in a larger geometry. In the same way, objects in free fall are following the straightest world lines they can through whatever space-time geometry exists. If mass and energy were not present, space-time would be flat. All these world lines would be straight in the four-dimensional sense, and gravity would never appear. But the universe is not empty. Every atom, every star, every galaxy carries energy and momentum. Einstein discovered that this content tells space-time how to curve. In response, space-time tells matter how to move, nudging those world lines away from what they would be in an empty universe. This is the key step in the story. Instead of saying Earth pulls on you, we will soon say Earth curves the space-time around it. Instead of saying the sun pulls planets into ellipses, we will say the sun creates a valley in space-time that planets follow like marbles. The math behind this is fierce, but the guiding picture is surprisingly gentle. Free fall is not the result of a force. It is an object loyally tracing the straightest path available through a bent four-dimensional landscape. In the next part, we will turn that abstract idea into sensations you actually feel and clocks you can hold in your hand. Think about the last time you tripped or jumped off a ledge for half a second. In that tiny moment between leaving the ground and landing, your stomach fluttered and the usual sense of heaviness faded. That feeling is your nervous system getting a brief taste of its natural state in Einstein's universe. Not pressed down, not held up, just falling along the path space-time prefers for you. The strange part is that this weightless state is the one that needs no explanation, while the heavy, normal feeling you have right now actually does. When you stand on the floor, it feels like gravity is pulling you down, and the floor is quietly doing nothing. General relativity flips that picture. Your body is trying to follow a geodesic, a natural straight path through curved space-time that heads toward Earth's center. The atoms in the floor resist that motion through electromagnetic forces. They push up on your feet push up on your legs, and that chain of resistance is the pressure you label as weight. Take the floor away, and that push vanishes. Gravity did not switch off. The resistance did. Imagine you are in a closed elevator again. Cable intact. The elevator is hanging motionless in a building shaft. You feel the floor under your shoes, the weight of your arms, the usual pressure in your knees. Now imagine someone instantly removes the cable and the elevator begins to drop. Nothing inside has a chance to react at first. The elevator, you, and the air all accelerate downward together. For a short time, you float in mid-air, your stomach lifting, objects hovering beside you. Your brain screams that gravity disappeared, but really you have simply stopped fighting the geodesic. Now picture a spacecraft orbiting Earth. It is still very much inside Earth's gravitational field. At the altitude of the International Space Station, gravity is only slightly weaker than it is on the ground. Yet astronauts drift around as if there is no gravity at all. The reason is the same as your falling elevator, stretched out into a circle. The station is in constant free fall toward Earth, but it is also moving sideways so fast that as it falls, Earth curves away beneath it. The result is a perpetual state of falling and missing, and everything inside shares that motion. Your body is an excellent detector of support forces. It is much worse at detecting gravity directly. You feel the chair pushing up on you, not some mystical downward pull. you feel the straps of a roller coaster, not the curvature of space-time. When those support forces vanish, your inner sense of gravity vanishes with them. That is why astronauts describe the shock of weightlessness, not the shock of suddenly feeling pure gravity. Free fall is silence for your pressure sensors. This idea leads naturally to another wild conclusion. If weight is a sign that something is pushing on you, then from the viewpoint of space-time, you are actually accelerating upward when you stand still on the ground. You are forced away from the geodesic you would otherwise follow. In contrast, a falling object with nothing touching it is not accelerating in its own frame. It is simply coasting through curved space-time. The everyday statement that falling needs a cause while standing does not is backwards once you look at the geometry. So far, we have talked about how gravity reshapes paths through space. Now we add the twist that makes relativity truly mind-bending. Gravity also reshapes time. Einstein realized that if space-time is one unified thing, then curvature can not only affect where you go, it must also affect how fast your clock ticks. The closer you are to a massive object, the more space-time is curved, and the slower time passes relative to someone farther away. This is not just a poetic metaphor. It is a hard, measurable fact. Imagine two identical, super-precise clocks. You keep one at sea level and carry the other up a tall mountain. The mountain-top clock is higher in the gravitational field, where space-time is slightly less curved. It ticks a tiny bit faster than the one in the valley. Bring them back together after some time and they will disagree by a tiny fraction of a second. Not because one malfunctioned, but because they truly experienced different amounts of time. In the 1970s, scientists tested this with atomic clocks on airplanes. They flew clocks around the world and compared them to clocks left on the ground. After the flights, the airborne clocks were out of sync by exactly the amount general relativity predicted. The difference was minuscule, measured in billionths of a second, but real and repeatable. Later experiments pushed this even further, measuring time dilation between two clocks separated by less than half a meter in height. Raise one clock by the height of your kitchen counter, and it will tick measurably faster than the one you leave on the floor. You rely on this effect being understood every time you use a navigation app. Global Positioning System satellites orbit thousands of kilometers above Earth. They are farther from the center of mass, where gravity is weaker and space-time is less curved. So their onboard atomic clocks tick slightly faster than clocks on the ground. At the same time, the satellites are moving fast, and special relativity says fast motion makes time run slower. The two effects partially cancel, but not completely. Engineers have to adjust the satellite clocks by many microseconds per day in advance. If they did not, your phone would quickly think you were kilometers away from where you actually are. Light itself feels this warping of time. A beam climbing out of a gravitational field loses energy. Since the energy of a photon is tied to its frequency, the light shifts to a lower frequency and a longer wavelength. That shift toward the red end of the spectrum is gravitational redshift. We see it in light escaping from dense stars, and in delicate laboratory experiments where photons traveling upward through Earth's field arrive ever so slightly redder than they started. It is time dilation written in color. Put all of this together, and the picture of reality becomes much richer than the simple pull you learned as a child. When you drop a ball, it accelerates not because a force reaches out and grabs it, but because its natural world line curves toward Earth in space-time. When astronauts float, they are closer to the pure state of unforced motion than you are as you sit listening to this. When you climb a staircase, you literally age a tiny bit faster than someone who stays downstairs because you spend more time in a region where gravity is weaker. General relativity invites you to see yourself not as a static object in a fixed arena, but as a moving point on a four-dimensional landscape where paths bend and clocks stretch. Gravity becomes the art of reading that landscape. In the next part, we will use that new perspective to follow beams of light as they swing around massive objects, reveal hidden matter, and let us map structures far beyond what any single telescope can see. So far, we have mostly talked about how gravity guides the motion of things with mass. Apples, planets, spacecraft, you. But in Einstein's picture, light is not exempt. Yet it must still live inside space-time, ride its curves, and respect its geometry. That raises a sharp question. In a universe where gravity is geometry, what happens to a beam of light that passes near something massive? The answer is deceptively simple. Light follows geodesics in spacetime just like everything else. In flat spacetime, that means straight lines. In curved spacetime, those straight lines become the closest thing to straight the geometry allows, which often look curved when you draw them in ordinary space. So if a massive object bends spacetime, any ray of light that passes by has its path tilted slightly as it tries to follow the local geometry. To you watching from far away, the beam appears to bend around the mass. Einstein worked out how much starlight should bend when it skimmed past the sundae. The effect was tiny. For a ray just grazing the solar surface, the apparent position of the background star would shift on the sky by less than 1,000th of a degree. You could never see that shift in broad daylight because the sun outshines everything around it. You need the sun to be in the sky and invisible at the same time. Nature offers that combination during a total solar eclipse. In 1919, 2 expeditions set out to test the prediction. Both teams prepared carefully calibrated photographs of the same star fields months earlier, when the sun was nowhere near them. Then, during the brief minutes of totality, they photographed the stars again near the darkened solar disk. Back home, they compared the plates. The apparent positions of the stars had shifted outward from the dark sun by exactly the tiny amount general relativity predicted. This was more than a neat measurement. It was a demonstration that the sun was not pulling on light with some mysterious force. It was reshaping the stage itself. Light was simply following the straightest paths in that warped space-time. Newspapers turned it into front-page news. Overnight, Einstein went from obscure theorist to global icon. For the first time, we had direct evidence that gravity bends light because it bends space and time. Once you accept that massive objects can deflect light, you might suspect that larger masses do it more dramatically. A single star gives a minuscule bend. A galaxy filled with billions of stars gives more. A cluster of galaxies, plus the dark matter holding them together, can bend light so strongly that it behaves like a cosmic lens. Astronomers call this gravitational lensing, and it is one of the most powerful ways we have to see the invisible. Picture a distant background galaxy sending its light toward us. Between it and us sits a massive cluster of galaxies. The cluster curves space-time in its neighborhood. Light from the background galaxy flows through that curved region, and its paths get redirected. Some rays are bent slightly, others more sharply. When that tangled bundle of light finally arrives at our telescopes, the background galaxy can appear distorted into arcs, smeared into long streaks, or even split into multiple images at different points around the cluster. To your eyes, the background galaxy looks warped, stretched, or copied. To the universe, nothing magical happened. Each photon simply took a different geodesic through the curved space-time created by the foreground cluster. The pattern of distortions is not random. It encodes information about how mass is distributed in the lensing object. By carefully analyzing the shapes and positions of these arcs in multiple images, astronomers can reconstruct where the mass must be inside the cluster. This is where lensing becomes a detective tool. When you add up all the visible matter in a cluster, the stars, the glowing gas, the galaxies themselves, you do not get enough mass to explain the strength of the lensing. The light is bent too strongly. Something unseen is contributing extra gravity. By mapping how the background galaxies are stretched around the cluster, scientists can draw detailed maps of that hidden mass. Those maps reveal vast halos extending well beyond the visible galaxies. We call this missing mass, dark matter. And gravitational lensing is one of the main reasons we are sure it exists. Sometimes the alignment between background galaxy, lens, and Earth is so precise that the background object gets smeared into a nearly complete ring around the foreground mass. These are called Einstein rings, a direct visual signature of space-time curvature. In other cases, a bright background quasar appears as 4 points of light arranged around a foreground galaxy, an Einstein cross. Each point is the same object seen along a different bent path. Light along each route travels a slightly different distance and passes through regions of slightly different gravitational potential. so the images flicker at different times when the quasar varies. Even the time delays between those flickers become data, helping us measure distances and the expansion of the universe. Gravitational lensing works on many scales. On the largest scales, weak lensing subtly distorts the shapes of millions of distant galaxies. A single galaxy looks almost unchanged, but when you look at huge statistical samples, you see a gentle preferred stretching pattern caused by the combined pull of enormous structures along the line of sight. This lets cosmologists trace the skeleton of the cosmic web, the filaments and nodes of dark matter that ordinary galaxies light up like beads on a wire. On smaller scales, lensing can briefly brighten a single background star when a compact object drifts in front of it. As the foreground object moves, its gravitational field focuses more or less of the background starlight toward us. This gravitational microlensing acts like a tiny natural zoom lens that switches on and off over days or weeks. In some cases, planets around the lensing star can add extra blips to the light curve, revealing their presence even if the star itself is too faint and distant to study in any other way. All of this bending and stretching pulls together the abstract pieces we have been building. Light travels on spacetime geodesics. Mass and energy curve spacetime. So by watching how light paths twist and split, we can map mass that does not shine, test general relativity on vast scales, and measure cosmic distances without relying on traditional yardsticks. Gravity is no longer just the thing that keeps planets in orbit. It becomes a tool for turning the universe itself into a telescope. At the same time, lensing hints at something more ominous. If enough mass in a small enough region can warp light into rings and arcs, what happens when mass is crushed even more tightly? How far can curvature go before spacetime effectively closes off from the rest of the universe? In the next part, we follow that question down into the most extreme gravitational objects we know, where even light cannot escape, and where our current theories begin to break. Follow the logic of gravity long enough and it eventually stops feeling gentle and elegant. It turns violent. If mass curves spacetime, you can ask a brutal question. What happens if you cram so much mass into such a small region that the curvature becomes inescapable? Not just strong, but absolute. That question leads directly to black holes, the most extreme objects general relativity allows. They are not cosmic vacuum cleaners sucking everything in. They are regions where space-time itself is so warped that every possible path leads inward. To understand how something like that forms, start with an ordinary massive star. For most of its life, a star is a delicate balance. On the one hand, gravity pulls everything inward, trying to crush the star into a dense ball. On the other hand, nuclear fusion in the core produces energy and pressure that push outward. As long as the core keeps fusing hydrogen into helium and then heavier elements, outward pressure and inward gravity match. The star sits in hydrostatic balance, neither collapsing nor flying apart. Eventually, the fuel runs low. In a sun-like star, once the core runs out of hydrogen, it contracts and heats until helium fusion starts. The star swells into a red giant, sheds its outer layers, and leaves behind a white dwarf, a dense ember supported by quantum pressure. They burn through hydrogen, helium, carbon, oxygen, silicon, and so on, fusing each element into heavier ones in a frantic series of stages. Each new fuel catches fire at higher temperature and pressure, each stage shorter than the last. At the end of that chain sits iron. Fusing iron does not release energy. It costs energy. Once the core fills with iron, fusion can no longer support the weight of the outer layers. Gravity wins in a catastrophic instant. The core collapses in a fraction of a second. Electrons are crushed into protons to form neutrons, and the outer layers rebound in a titanic supernova explosion that can briefly outshine an entire galaxy. The scattered debris seeds space with heavy elements. The collapsed core is left behind as a neutron star. Neutron stars are already extreme. Take more than the mass of our sun, pack it into a sphere about 20 kilometers across, and you get densities where a teaspoon of matter would weigh 1 billion tons. Surface gravity is hundreds of billions of times stronger than Earth gravity. Light climbing away is heavily redshifted. In some cases, beams of radiation from the magnetic poles sweep across space, and we see them as regular pulses from pulsars. These objects are so compact that they bend space-time significantly. But there is still a surface. In principle, you could point to where the star ends and empty space begins. If the collapsing core is even more massive, roughly more than 3 times the mass of our Sun, not even neutron pressure can resist gravity. There is no known form of matter that can hold itself up. The collapse does not stop. The mass plunges inward until, in the mathematics of general relativity, it shrinks to an infinitely small point, a singularity. Around that singularity, space-time curves so fiercely that there is a closed boundary, the event horizon, beyond which nothing that crosses can ever come back out. The size of that event horizon depends on how much mass is inside. For a black hole with the mass of our Sun, the radius of the horizon would be about 3 kilometers. A 10 solar mass black hole would have a horizon around 30 kilometers. A supermassive black hole with 1 billion solar masses, like the ones at the centers of big galaxies, would have an event horizon roughly 3 billion kilometers in radius, large enough to swallow the orbit of Saturn. Same basic object, different scale of abyss. From the point of view of someone falling in, crossing the event horizon is uneventful. If the black hole is large enough, tidal forces at the horizon are mild. You drift across in a finite amount of time, then continue inward. You might not even notice the exact moment when you pass the point of no return. From far away, an outside observer sees something very different. As you approach the horizon, time dilation grows extreme. Your clock appears to tick slower and slower. Light you send out is stretched to longer wavelengths, shifting from visible to infrared to radio and fading. To that distant observer, you never quite reach the horizon. You freeze and dim, seemingly stuck just outside forever. This strange disagreement is a matter of perspective, not a contradiction. For you, your future inside the horizon is as certain as your future in normal space-time. Outside, your friends can never see that part of your story, because no signals can climb back out. Inside, space-time is so warped that the direction we call inward is not just a place. It becomes a direction in time. Just as you cannot stop moving toward tomorrow, you cannot stop moving toward the singularity once you are inside. The singularity is not a location you can dodge by sidestepping. It is a moment in your personal future that you cannot avoid. Before you get that far, tidal forces can become murderous. Gravity is a bit stronger on the parts of you closer to the black hole, and weaker on the parts farther away. On Earth, that differential produces gentle ocean tides. Near a compact black hole, it stretches objects into long, thin strands. Fall feet first toward a small black hole, and your feet feel a stronger pull than your head. You are stretched and squeezed, in a process physicists with a dark sense of humor call spaghettification. For stellar mass black holes, this would shred you before you even reach the horizon. For supermassive black holes, the horizon is far enough from the center that you might cross intact and only be torn apart much deeper in. For a long time, black holes were thought of as perfectly black, swallowing anything that crossed the horizon and never giving up information or energy. Then, in the 1970s, Stephen Hawking combined quantum mechanics with general relativity in a clever way near the horizon, and found that black holes should actually emit a faint glow, now called Hawking radiation. The rough idea is that empty space is not truly empty. Quantum fields produce pairs of particles and antiparticles that pop into existence and annihilate almost immediately. Near an event horizon, one member of a pair can fall in while the other escapes to infinity. To an outside observer, it looks as if the black hole has emitted a particle. That emission carries energy away, which means the black hole loses mass and very slowly shrinks. A solar mass black hole would take an absurdly long time to evaporate. The estimated lifetime is around 10 to the power of 67 years, which is a 1 followed by 67 zeros. The universe today is only about 10 to the power of 10 years old. Supermassive black holes would last even longer. On any human or even cosmic timescale, they are effectively permanent. Small black holes, if they exist, would evaporate more quickly. A black hole with the mass of a mountain could vanish in roughly 1 billion years. A black hole with the mass of a big ship would explode in a fraction of a second, converting its mass into an intense burst of radiation comparable to multiple nuclear bombs. We have never seen such an event. We have never even confirmed that tiny primordial black holes exist. They are a possibility, not an observed reality. Still, Hawking radiation changes the story. Black holes are not completely black, and their evaporation raises deep questions about what happens to information that falls in. All of this leads us back to the singularity itself, the place where space-time curvature becomes infinite in the equations. Infinite curvature and infinite density are usually the universe hinting that your theory has reached its limits rather than describing something literal. Many physicists suspect that at incredibly small scales, near what is called the Planck length, space-time may no longer be smooth. It might be made of fundamental discrete chunks, a kind of quantum foam where the familiar ideas of distance and duration lose their meaning. In such a picture, the singularity would not be a point of truly infinite density, but a region where our current language simply cannot be applied. There is another layer of mystery called cosmic censorship. Roger Penrose proposed that singularities in general relativity are always hidden inside event horizons. In other words, nature censors naked singularities that would be visible from the outside. If they existed out in the open, light from regions where the laws of physics break down could reach us, making the universe unpredictable in a deep way. Some exotic mathematical solutions seem to produce naked singularities, but nobody knows if the real universe ever allows them. Black holes sit at the edge of our understanding. They are born from the same gravity that lets apples fall. Yet they push that gravity to a place where general relativity becomes both stunningly accurate and clearly incomplete. We can describe the horizon, the orbits around it, the way light bends, and the way matter spirals in. We cannot describe the ultimate fate of information at the singularity without a full theory of quantum gravity. In the next part, we watch these monsters collide and listen to the ripples they send through space-time, ripples that we have only recently learned to detect directly. Up to now, gravity has mostly been about shapes. Curved space-time guiding orbits, bending light, swallowing matter in black holes. But curves do not have to sit still. They can move. If mass and energy tell space-time how to curve, then changing mass distributions should send that curvature rippling outward. The question is whether those ripples are real things that can be felt and measured, or just mathematical decorations on Einstein paper. For a long time, they were a theoretical whisper. Then we learned to listen. Einstein himself realized that accelerating masses ought to produce waves in space-time, not waves in some medium floating in space, but literal ripples of stretching and squeezing built into the geometry. Imagine two neutron stars orbiting each other. Their intense gravity churns space-time around them. As they whirl faster and faster, they should radiate energy away through gravitational waves. That lost energy has to come from somewhere, so the stars spiral closer together over time. Without ever seeing the waves directly, you can still see their fingerprints in the way the orbit slowly decays. In the 1970s, Russell Hulse and Joseph Taylor found exactly such a system. A binary pulsar, two neutron stars locked in a tight orbit. One flashing radio pulses past Earth with clock-like regularity. By tracking the timing of those pulses over years, they could see the orbit shrinking. The period between closest approaches was getting shorter at a rate that matched Einstein's prediction for energy lost to gravitational radiation. No other explanation fit the data as cleanly. It was indirect, but it was strong evidence that space-time really does radiate when massive objects dance violently enough. Still, indirect evidence is not the same as hearing the waves themselves. To detect them directly, you need instruments that can sense absurdly small changes in distance. A passing gravitational wave stretches space in one direction while squeezing it at right angles, then reverses, over and over. If you had two long perpendicular tunnels and bounced lasers back and forth along them, a wave passing through would change the lengths by a tiny amount. The challenge is that tiny here means smaller than the size of an atomic nucleus over kilometers of distance. Thermal vibrations, trucks on nearby roads, even waves crashing on distant coastlines all threaten to drown out the signal. The Laser Interferometer Gravitational Wave Observatory, usually called LIGO, was built to take on that challenge. It consists of two facilities in the United States, one in Louisiana and one in Washington state, separated by about 3,000 kilometers. Each site has two arms, 4 kilometers long, arranged in an L shape. A powerful laser is split and sent down each arm, bounced between mirrors, then recombined. In perfectly quiet spacetime, the beams line up in a very specific way. If a gravitational wave passes, it stretches one arm and squeezes the other by a minute amount, shifting the pattern of light where the beams meet. The sensitivity is almost ridiculous. When LIGO made its first detection, the change in arm length was about 1/10,000th of the diameter of a proton. That is like measuring the distance to the nearest star with an accuracy better than the width of a human hair. To reach that precision, the mirrors hang from elaborate vibration isolators. The vacuum tubes are some of the largest in the world. Every known source of noise is hunted down and minimized. Then, after years of engineering and patient upgrades, in September of 2015, a signal swept through both detectors within milliseconds of each other. The waveform looked like a brief chirp, a low rumble that quickly rose in frequency and amplitude, then cut off. By comparing that shape to detailed computer simulations, scientists could reconstruct the event that caused it. Two black holes, one about 29 times the mass of the Sun and one about 36 times the mass of the Sun, had been orbiting each other in a distant galaxy. As they spiraled closer together, they orbited faster, tens and then hundreds of times per second. At the very end, they merged into a single black hole, about 62 solar masses in size. If you add 29 and 36, you get 65, not 62. They were converted entirely into gravitational wave energy in a fraction of a second, following the famous relation between mass and energy that Einstein discovered earlier in his career. During that blink of time, the power carried by the waves exceeded the combined light output of all the stars in the observable universe. Those waves traveled for more than 1 billion years, stretching and squeezing space as they went, until they nudged LIGO mirrors on a small planet and announced their presence as that brief chirp. This was more than a technical feat. It was a new sense organ for humanity. Since that first event, LIGO and its European partner Virgo have detected many more mergers, mostly black hole pairs and some neutron star collisions. Each detection is a new example of extreme gravity in action, letting us test general relativity in regimes that were pure theory before. The signals are not identical. They carry information about the masses of the objects, their spins, how circular or elongated their orbits were, and how far away the mergers occurred. By listening closely, physicists can read these details from the shape of each wave train. When two neutron stars merge, the story becomes even richer. Neutron stars are made of matter, squeezed to densities where normal atomic structure collapses. Different theories of how matter behaves under those conditions predict slightly different ways the stars squish and wobble in the final orbits before merging. That in turn changes the fine structure of the gravitational wave signal. By comparing observed signals to models, scientists can infer how compressible neutron star matter is, putting constraints on the mysterious equation of state that describes ultra-dense matter. It is like doing an experiment on material that exists nowhere on Earth by watching distant stellar corpses collide. One famous neutron star merger in 2017 did something extra special. The gravitational wave signal was picked up first, and then, seconds later, satellites detected a burst of gamma rays from the same direction in the sky. Over hours and days, telescopes across the world saw a fading afterglow in visible light, X-rays, and radio waves. For the first time, astronomers observed a single cosmic event through both gravitational waves and traditional electromagnetic radiation. This multi-messenger observation showed that such mergers are factories for heavy elements like gold and platinum. Gravitational waves also test the foundations of gravity theories themselves. In general relativity, these waves travel at exactly the speed of light. Some alternative theories predict slightly different speeds. By comparing the arrival time of gravitational waves from that neutron star merger with the arrival of gamma rays, scientists showed that any difference in speed must be incredibly tiny. Whole families of modified gravity theories were ruled out. Every detection so far has lined up with Einstein equations, even as we probe more exotic systems. Looking ahead, new detectors will open different parts of the gravitational wave spectrum. Ground-based observatories are being upgraded, and new ones are being built in other countries. In space, a planned mission will fly 3 spacecraft in a triangular formation millions of kilometers apart, sensitive to lower frequency waves from supermassive black hole mergers in galactic centers. Together, these instruments will allow us to hear events across a huge range of masses and timescales, from stellar remnants to monsters millions of times the mass of the Sunday. What began as subtle ripples predicted on paper has become a practical way to explore the universe. Gravitational waves slip through matter almost unhindered. They carry news from places that light struggles to escape, like the core of a collapsing star or the final orbits deep in a strong gravitational well. With them, we are no longer limited to what the universe shines at us. We can listen to what it shakes into space-time itself. In the next part, we bring this grand, dynamic picture back down to the neighborhood of Earth and the solar system, connecting these cosmic waves and curves to the structure and history of the worlds we know best. For a while, we have been riding black holes and surfing gravitational waves. Let us come home for a bit. Gravity might feel most ordinary here on Earth, but this is where you can actually see what space-time curvature does to rock, air, and oceans. Every mountain range, every breath of air you take, even the shape of our planet, is a long-term side effect of matter trying to follow geodesics while also colliding, heating, and resisting. To really feel what gravity is, you do not need a galaxy. You just need to look under your feet and slightly up. Start with the simplest question. Why does Earth have an atmosphere when some other worlds do not? Air is made of molecules bouncing around at high speeds. Left alone, they would fly off in straight lines and never return. Gravity curves their paths into arcs that loop back toward the planet. If the pull is strong enough and the molecules are not too hot, they remain bound, forming an atmosphere that hugs the world. If the gravity is weaker or the air gets heated for long enough, the fastest molecules can escape one by one, and the atmosphere thins over time. Compare Earth and Mars. Earth is larger and more massive, so its escape speed is higher. Molecules in our atmosphere need much more energy to break free. Over billions of years, solar radiation and charged particles from the solar wind kicked many of Mars' lighter atmospheric molecules over that escape threshold. Gravity could not hold on to them. Today, Mars has only a thin wisp of air, while Earth keeps a deep, dense atmosphere where complex weather and life can exist. The pull toward Earth's center does more than hold air. It shapes the entire interior. Early in Earth's history, when the young planet was still molten, gravity pulled heavier elements inward. Dense metals like iron and nickel sank, forming a core. Lighter silicates floated upward to make the mantle and crust. This process, called differentiation, was gravity sorting matter by density in slow motion. Once things cooled, the interior solidified in layers. A solid inner core, a liquid outer core, a slowly creeping mantle, and a brittle crust riding on top. The motion inside never really stopped. The outer core is made of liquid metal that moves and swirls. Those flows, driven by heat and rotation, generate Earth's magnetic field. That invisible shield deflects much of the charged particle storm from the sun, protecting the atmosphere and life on the surface. Gravity is the reason the core exists in the first place. Without enough mass to compress and heat the interior, you would not get molten metal and you would not get a global magnetic shield. The shape of space-time around Earth quietly helps decide how much surface life gets blasted by space weather. Higher up, in the mantle, rock that seems solid on human timescales behaves like an extremely thick fluid over millions of years. Heat from radioactive elements and leftover formation energy makes hot material slowly rise, while cooler material sinks. Gravity provides the direction of down that this circulation follows. Those mantle currents drag pieces of the crust along. Where plates collide, mountains rise. Where they pull apart, new ocean floor forms. Where one plate dives under another, deep trenches open and volcanoes erupt. Plate tectonics is gravity plus heat acting on rock that is almost, but not quite solid. Even the simple fact that mountains are not infinitely tall is a gravitational argument. Rock has a limited strength. Build a mountain too high, and its own weight causes its base to flow outward and down, slowly reducing the peak. There's a balance between uplift from plate motions and collapse under weight. On worlds with weaker gravity, like Mars, tall volcanoes can grow larger before that balance breaks. The giant shield volcano Olympus Mons rises about 3 times higher than Everest because Martian gravity is weaker and the lithosphere can support bigger structures before failing. Now zoom out to the scale of the solar system. The Sun contains more than 99% of the total mass. Its gravity dominates the shape of space-time in this neighborhood. Planets, comets, and asteroids are all following geodesics in that curved space-time. Seen from far away, those geodesics look like the familiar near-circular or elliptical orbits you see in diagrams. From the standpoint of general relativity, an orbit is just a constant state of sideways freefall in the valley carved by the Sun's mass. Each planet also carves a smaller dimple on top of the Sun's overall curvature, which is more massive than all the other planets combined, sculpts the region of space around it in a dramatic way. In the asteroid belt, there are gaps where almost no asteroids live. These are called Kirkwood gaps. They correspond to orbits where an asteroid would circle the Sun in a time that is a simple fraction of Jupiter's orbital period. In those spots, the asteroid would get a regular gravitational tug from Jupiter at the same point in its path. Over many millions of years, those repeated nudges push the rock into a different orbit, clearing out the gap. The same resonant story plays out in Saturn's rings, just on a finer scale. The rings are made of countless chunks of ice and rock, from dust-sized grains to boulders, all orbiting in a flat disk. Yet the rings are not uniform. They have gaps, sharp edges, and braided structures. Some of those features exist because small moons called shepherd moons orbit just inside or outside certain ring regions. Their gravity gently herds particles, keeping ring edges crisp and maintaining gaps. Other gaps align with orbital resonances between ring particles and larger moons farther out. Once again, periodic gravitational tugs rearrange matter into ordered patterns. Gravity also reaches far beyond the planets we usually name. Surrounding the solar system, probably extending to distances of around 1 light-year, there is a vast cloud of icy bodies known as the Oort cloud. Most of those comets sit in quiet, slow orbits. Occasionally, a passing star or the tidal gravity of the Milky Way itself disturbs one of them. Its orbit slowly changes, until the geodesic it follows carries it inward toward the Sunday. As it approaches, sunlight warms its surface, ices vaporize, and a glowing tail forms. To you on Earth, it appears as a sudden visitor from the deep dark. But its long fall inward is just space-time geometry plus time. Sometimes that geometry delivers a more dramatic show. In the 1990s, astronomers watched a comet called Shoemaker-Levy 9 get torn apart by Jupiter's tidal forces. The comet had strayed too close. The difference in gravity across its length exceeded the strength of the ice and rock holding it together, and it broke into a chain of fragments. A short time later, those fragments plunged into Jupiter's atmosphere one by one. Each impact released energy comparable to millions of nuclear weapons. Dark bruises appeared in the planet clouds, visible for months. This was gravity in action, as both sculptor and executioner, rearranging orbits and pulverizing anything unlucky enough to cross certain boundaries. From Earth's interior to Saturn's rings to the distant Oort cloud, the same principle keeps resurfacing. Mass curved space-time. Objects follow geodesics in that curved space-time, unless forces like pressure or material strength push them away. Air molecules orbit Earth, entangled, colliding paths, and become air. Plates ride up and down in slow convective currents and become continents and oceans. ice chunks dance in the gravitational field of Saturn and become rings. Comets wander in the outskirts and occasionally dive sunward, transforming into spectacular sky events or violent impacts. Seen this way, the solar system stops being a static collection of balls on a black background and becomes a living network of flows, collisions, and long falls. Gravity is the quiet engine behind nearly every large-scale pattern. In the next part, we will step back again and let gravity build entire generations of stars, blow them apart, and recycle their ashes into new worlds and into you. Look up at the night sky for a moment in your mind. To get a star, you have to take cold, dark gas spread out over light years and make it collapse until the center is hot enough for atoms to fuse. Left to themselves, gas clouds would drift forever. Gravity refuses to let that happen. It slowly amplifies the tiniest imbalance into a runaway collapse that lights up the universe. The story begins inside giant molecular clouds. These are vast regions of gas and dust, hundreds of light years across. So cold that hydrogen molecules huddle together and starlight barely gets through. Most of the time, nothing dramatic is happening. The cloud is in rough balance, pressure pushing outward, gravity pulling inward. Then somewhere in that gloom, a region becomes just a little denser than average. Maybe a previous supernova shockwave nudged it. Maybe gravity itself gathered a bit more mass there by chance. Once that patch is denser, its gravity pulls more strongly on nearby material. That extra material makes it denser still, which increases its gravity again. A feedback loop begins. Over millions of years, the region contracts, fragments, and forms clumps. Each clump is slowly falling in on itself. As gas falls inward, it converts gravitational potential energy into heat. The center of each collapsing clump gets hotter and hotter even as the outer layers continue to fall. At first, radiation from the forming protostar can escape fairly easily, and the collapse continues. Eventually, the central region becomes so dense that radiation is trapped for a while. Heat builds up, pressure rises, and the collapse slows. In the very center, temperatures climb to millions of degrees. Hydrogen nuclei, which are just protons, move fast enough to overcome their mutual electrical repulsion and fuse into helium. When that first fusion reaction happens, a star is born. From that moment on, the life of the star is a wrestling match between gravity and pressure. Gravity always tries to pull everything inward. It does not explode outward, and it does not collapse inward. Our sun has been in that quiet, balanced phase for about 4.5 billion years, and will stay there for roughly that long again. The mass of the star decides its entire future. Low-mass stars burn their fuel slowly, shining steadily for tens or even hundreds of billions of years. The universe is not even old enough for any of them to have finished their lives yet. Medium-mass stars like the Sun live shorter lives on the order of 10 billion years. Very massive stars burn hot and fast. They pour out light and wind so intensely that they race through their fuel in only a few million years. As hydrogen in the core runs out, the balance tips. Fusion slows, so pressure drops, and gravity starts to win. The core contracts and heats up again, until a new fuel catches fire. Helium begins to fuse into carbon and oxygen. The outer layers expand and cool, turning the star into a red giant. In a sun-like star, this expansion will eventually engulf the inner planets. Earth itself will likely be baked and stripped long before that final phase is complete. In stars a bit more massive than the Sun, the chain continues. After helium burning, under greater pressures and temperatures, carbon can fuse into heavier elements like neon and magnesium. In even more massive cores, fusion marches all the way up the periodic table. A massive star might spend millions of years fusing hydrogen, but only days fusing silicon near the end. Iron is a dead end in this process. Fusing elements lighter, then iron releases energy. Fusing iron absorbs energy. Once the core fills with iron, and iron-like nuclei, the star loses its main source of outward pressure. Gravity does not take long to notice. Within a second, the core collapses. Densities soar past anything ordinary matter can support. Protons and electrons are crushed together to form neutrons, and the core slams to a stop at nuclear densities. The outer layers, still plunging inward, bounce off this suddenly rigid core. That bounce, aided by intense floods of neutrinos streaming out from the core, drives a shockwave through the star. The entire outer envelope is blasted into space at a few percent of the speed of light. For weeks, the supernova outshines the entire host galaxy. The debris from that explosion carries heavy elements into the surrounding interstellar medium. Calcium, iron, nickel, and many other elements that did not exist before are now mixed into the gas between stars. The crushed core left behind is a neutron star if the mass is in the right range. Imagine more than the sun mass squeezed into a sphere about 20 kilometers wide. The density is so extreme that atomic nuclei disappear, neutrons packed together in a gigantic quantum object. Surface gravity is hundreds of billions of times stronger than Earth gravity. If you could somehow stand on the surface, which you cannot, you would be instantly flattened into a layer only atoms thick. Light climbing away from that surface loses a significant fraction of its energy and shifts toward the red. Many neutron stars spin rapidly and have powerful magnetic fields. As the star rotates, these beams sweep around like lighthouse beams. If one of those beams passes across Earth, we see a regular sequence of pulses at radio or X-ray wavelengths. Their ticking is so stable that astronomers use them to test general relativity and, in groups, to search for very low-frequency gravitational waves stretching across the galaxy. If the core left behind after collapse is even more massive, there is no stable neutron star configuration. Gravity presses onward. The core falls through its own event horizon and a black hole forms. That is the branch of the story we explored earlier. From the star's point of view, it has simply run out of ways to push back. Gravity has won completely. Yet even in that extreme victory, gravity is setting up material that will influence future generations of stars and planets. The key idea is that supernovas and neutron star mergers throw heavy elements into space. Those elements do not stay in one place. Over millions of years, they mix with the surrounding hydrogen and helium gas. The next generation of molecular clouds that collapse under gravity carry those metals as impurities. When they form new stars and planets, those heavy atoms end up in rocky worlds, in atmospheres, and eventually in living cells. The carbon in your DNA, the calcium in your bones, the iron in your blood, all were forged in ancient stars and scattered by explosions or collisions, long before Earth formed. Gravity pulled together the gas that made those stars, held them together while fusion ran, then crushed their cores and flung their outer layers into space. Later, gravity pulled that enriched gas into a new collapsing cloud that became our sun and its planets. You are literally part of a cosmic recycling program, run by gravity over billions of years. When you hear the phrase, "we are made of star stuff," this is what it means. Gravity gathers diffuse gas. Fusion inside stars cooks new elements. Explosions and mergers spread those elements. Gravity gathers them again into new structures, over and over, each cycle adding complexity and richness to the material of the universe. Without gravity, there would be no stars, no heavy elements, no rocky planets, no chemistry that can build something as intricate as a living brain listening to this sentence. So far, we have followed gravity as it sculpts individual stars and recycles their ashes. In the next part, we zoom out once again to see how gravity assembles hundreds of billions of stars into galaxies, anchors supermassive black holes at their hearts, and stretches those galaxies into an enormous cosmic web that spans the visible universe. By now, we have watched gravity light stars, crush their cores, and fling their ashes back into space. The next question is, what happens when you give gravity a whole universe of time and a vast sea of gas to play with? The answer is galaxies. Not just a few scattered islands of stars, but a staggering tapestry of hundreds of billions of them, woven into an enormous three-dimensional web. From far enough away, gravity turns the universe into something that looks almost like a neural network of light. The seeds of galaxies were tiny ripples in the density of the early universe. After the hot, smooth beginning, there were places that were just a little denser than average. Not much, parts in 100,000. Those slightly denser regions pulled a little harder on nearby matter. Over millions of years, that extra pull made them denser still. The pattern is the same one we saw in star-forming clouds, just on a scale far beyond any single cloud or star. Gravity takes small differences and amplifies them. There is a twist. The matter doing most of the pulling at these early times was not the ordinary atoms that make up you and me. It was dark matter, some unknown kind of mass that does not emit light or interact strongly with it. Dark matter feels gravity and creates gravity, but it does not glow or absorb in any wavelength we can see. In the young universe, dark matter collapsed first into huge clumps. Ordinary gas fell into the gravitational wells of those clumps, cooled, and began forming stars. Each dark matter halo with its swarm of stars is what we now call a galaxy. Our own Milky Way is one of these structures. It is a spiral galaxy, about 100,000 light-years across, containing on the order of a few 100 billion stars. At its center sits a supermassive black hole with a mass of a few million suns. We know it is there because we can watch individual stars whipping around an invisible point in tight orbits that take only a few years. They move so fast and so close that the only way to explain their paths is a compact mass millions of times heavier than our sun packed into a region smaller than our solar system. That central black hole is not just a curiosity. It anchors the galaxy in an important way. Gas clouds that wander too close are shredded and heated, lighting up as bright flares. In some galaxies, matter falling into the central black hole powers jets that blast out for thousands of light years. These jets can heat surrounding gas and regulate how quickly new stars form. Once again, gravity couples things that feel very distant. The way matter spirals into a point at the center can shape the growth and appearance of an entire galaxy. The stars in a galaxy do not orbit any old way. Based on the visible matter alone, you would expect stars far from the center to move more slowly, the way planets in the outer solar system move more slowly than the inner ones. In many galaxies, they do not. Their rotation speeds stay high, all the way out into the faint outer regions. Something unseen must be providing extra gravitational pull to keep those stars bound. This is one of the strongest clues that dark matter halos surround galaxies. A massive, roughly spherical cloud of invisible matter extends far beyond the visible disk. The stars you see are just the bright core of a much larger gravitational structure. When you combine rotation curve measurements with gravitational lensing maps, which we talked about earlier, a consistent picture emerges. Most of the mass in galaxies is dark. Ordinary atoms are the decorative frosting on a dark matter cake. Galaxies themselves are rarely isolated. Our Milky Way belongs to a small collection known as the Local Group. It includes the Andromeda Galaxy, several other modest spirals, and dozens of dwarf galaxies. All of them orbit within a larger dark matter halo that holds the group together. Gravity continues its long, slow work here. The Milky Way has been steadily tearing apart and swallowing some of its smaller neighbors. Long, faint streams of stars arc around our galaxy, the remnants of dwarfs that strayed too close and were pulled apart. In roughly 4 billion years, the Milky Way and Andromeda will collide. Not like two billiard balls, but like two swarms of bees moving through each other. The stars themselves are so far apart that very few will collide. Instead, their orbits will be radically rearranged by the combined gravitational field. Gas clouds will ram into one another, compress, and trigger new waves of star formation. Over hundreds of millions of years, the neat spiral patterns will distort into tidal tails and bridges, then settle into a more rounded, merged galaxy with a single larger supermassive black hole at its center. Gravity loves mergers. This is how galaxies grow. Beyond small groups lie clusters. The Virgo cluster, for example, contains more than 1,000 galaxies. Within a cluster, galaxies orbit a common center of mass, swim through hot intracluster gas, and interact through mutual gravity and occasional collisions. Dark matter, again, dominates the mass budget. By studying gravitational lensing of background galaxies through these clusters, astronomers have mapped where the mass really sits. The result is always the same: huge dark halos, with galaxies sprinkled through them like bright knots. Take one more step back, And you see that clusters themselves are not scattered at random either. On the largest scales we can map, galaxies and clusters trace out a vast cosmic web. Long filaments of galaxies stretch across tens and hundreds of millions of light years. These filaments intersect at nodes where large clusters live. Between them are enormous, underdense regions called voids, places where there is relatively little matter. This web grew out of the same tiny early fluctuations we mentioned before. Regions that started slightly denser accumulated more matter as the universe expanded. Over billions of years, gravity amplified those small ripples into the striking pattern we see today. Computer simulations of structure formation, which evolve billions of particles under gravitational attraction in an expanding universe, produce webs that look uncannily like the observed one. This is a huge success of the idea that gravity, acting on dark matter and normal matter in an expanding space-time, is enough to build the large-scale structure of the universe. From the perspective of general relativity, all of this is geometry at work. The presence of matter and energy curves space-time. On galactic scales, that curvature guides stars around their orbits and keeps disks and halos intact. On cluster and cosmic web scales, it guides entire galaxies and clusters into filaments and nodes. It winds its way through a landscape of valleys and hills in space-time carved by all that mass, arriving slightly deflected and delayed compared with a fictional flat universe. We live inside one of the filaments of this web, in a modest galaxy with a growing central black hole, surrounded by an invisible halo we only know through its gravity. The shape of that halo decides how our galaxy interacts with its neighbors. The cluster our group is falling toward helps determine our long-term motion through the universe. The overall distribution of matter and energy controls not just where things are, but how the expansion of the universe itself evolves. In the next part, we will follow that thread all the way back toward the beginning, to see how gravity and expansion fit together in the story of the Big Bang, dark energy, and the ultimate fate of the cosmos. We have been treating gravity mostly as the sculptor of things that already exist. Now it is time to ask a harder question. What is gravity doing to the universe as a whole? Not just inside the web, but to the entire stage itself. The answer is unsettling. Space is not sitting there while galaxies move through it. Space is stretching. The gaps between galaxies grow with time, and gravity both drives and resists that expansion in ways that decide the entire future of the cosmos. The first clue came in the early 1900s. When astronomers studied the light from distant galaxies, they found that almost all of them looked slightly redder than expected. Their spectral lines, those sharp fingerprints of chemical elements, were shifted toward longer wavelengths. The simplest interpretation is that these galaxies are moving away from us. Their light is stretched as space between us and them grows while it travels. The farther away a galaxy is, the more its light is redshifted, and the faster it seems to recede. This relation between distance and recession speed was mapped out by Edwin Hubble and others. It is not that we sit in a privileged center and everything is fleeing from us personally. In every direction, from every galaxy, observers would see roughly the same pattern. The picture that fits the data best is that space itself is expanding everywhere. Imagine dots drawn on the surface of a balloon. As you inflate the balloon, every dot moves away from every other. Not because they crawl across the surface, but because the surface itself stretches. If the universe is expanding now, logic lets you run the movie backward. In the past, everything must have been closer together. Keep rewinding, and the densities rise. Galaxies converge into a hot fog of gas. Earlier still, atoms are ripped apart into a plasma of free electrons and nuclei. Earlier still, even that plasma was squeezed into a nearly smooth, unimaginably hot soup of fundamental particles. At some finite time in the past, everything we can observe was compressed into an extremely dense, hot state. That is what cosmologists mean by the Big Bang. Not an explosion in empty space, but the rapid expansion of space itself from a much denser beginning. Three major lines of evidence support this view. When you run the equations of general relativity backward, an expanding universe naturally emerges from them under very general conditions. Einstein once added a mathematical term to his equations to force a static universe. But when Hubble observations came in, he abandoned that adjustment and called it his greatest blunder. Third, the Big Bang model predicts two things that we can measure very precisely. One prediction is that the early universe, when it was only minutes old, should have forged light elements in very specific proportions. When the universe was incredibly hot and dense, protons and neutrons smashed together in a brief period of primordial nuclear fusion. That process should have left the cosmos with mostly hydrogen, a large fraction of helium, and small traces of lithium and beryllium. When astronomers measure the abundances of these elements in very old, nearly pristine gas clouds, they match those predictions. The other key prediction is that the universe should be filled with faint afterglow light from a time when it first became transparent. Early on, the hot plasma of electrons and nuclei scattered light constantly. Photons could not travel far without bouncing off charged particles. As the universe expanded and cooled, electrons settled into atoms. Suddenly, the fog cleared, and light could stream freely. That flash has been stretching with the universe ever since. Today, we see it as a nearly uniform sea of microwave radiation coming from all directions. This is called the cosmic microwave background. When satellites map this microwave sky in detail, they find it is astonishingly uniform, the same temperature to within tiny fluctuations. Those tiny hot and cold spots are the fingerprints of the same initial density ripples that later grew into galaxies and clusters. The pattern of those fluctuations matches what you get when you take general relativity, add a hot early universe, and let it expand for about 13.5 billion years. Cosmology is not just a story. It is a story with exquisitely measured numbers. This raises an obvious question. How big is this expanding universe? The part we can see is limited by how far light has had time to travel since the Big Bang. That region is called the observable universe. Its diameter is about 90 billion light-years. Beyond that, there may be more space that light has not reached us from yet. Space might go on forever, or it might curve back on itself in some huge loop. Our best measurements suggest that on large scales, the universe is very close to spatially flat, which is consistent with infinity, but does not prove it. The truth might be an immense but finite cosmos, or an endless one. Right now we cannot tell. General relativity also lets us ask how the expansion changes with time. If there were only matter in the universe, and no other weird ingredients, gravity would slow the expansion down. Galaxies would still be moving apart, but their recession speeds would gradually shrink. Eventually, if there were enough matter, gravity could halt the expansion and pull everything back together in a big crunch. If there were too little, the expansion would go on forever, slowly coasting to a halt as matter thins out. In the late 1990s, astronomers used distant exploding stars, called supernovas, as standard candles to measure how fast the expansion was changing. These particular supernovas are bright enough to be seen across billions of light-years and behave in consistent ways. When researchers compared their brightness and redshifts, they expected to see signs of a slowing universe. Instead, they saw the opposite. The expansion is speeding up. Something is pushing space apart, counteracting gravity on the largest scales. We call this something dark energy. It does not appear to clump like matter. It does not glow. In the simplest models, it is a property of space itself, a kind of constant energy density that does not dilute as the universe expands. Add more space, and you get more dark energy, which drives faster expansion, which creates more space. A runaway feedback built into the vacuum. When we tally up the total energy content of the universe, using cosmic microwave background maps, galaxy surveys, and supernova data, we get a wild result. Only a small slice, about 5%, is ordinary matter like atoms. Roughly a quarter is dark matter, some unknown mass that clusters and provides gravitational glue, but does not interact with light. The remaining slice, about 2/3, is dark energy, which drives accelerated expansion. In other words, about 95% of the universe is made of stuff we do not yet understand in detail. This has deep implications for the future. If dark energy behaves as a constant property of space, the acceleration will continue. Distant galaxies will recede faster and faster. Over very long times, their light will redshift so much that it becomes undetectable. They will slip beyond a kind of cosmic horizon, forever out of causal contact with us. Trillions of years from now, an astronomer in our galaxy would see only a handful of nearby galaxies, all merged into one big structure, floating in an apparently empty universe. The evidence that we now use to infer the Big Bang and expansion would be gone from view. Cosmology, as we practice it today, would be impossible. The ultimate long-term fate in that scenario is sometimes called heat death. Star formation gradually shuts down as gas is used up or blown away. Existing stars burn out. White dwarfs cool. Neutron stars and black holes remain. Over fantastically long times, even black holes evaporate through Hawking radiation. What is left is a thin bath of low-energy particles and radiation in ever-expanding space. No free energy gradients remain to power complex structures. The universe still exists, but it is quiet. That bleak future is so far away that it might as well be eternity from your perspective. The more interesting point for you is that we live at a special observational moment. The universe is old enough for galaxies, planets, and life to exist, but young enough that the cosmic microwave background is still visible. Distant galaxies are still within view, and the expansion history is still encoded in the sky. We can ask questions about beginnings and large-scale structure, because we appear at a time when gravity and expansion have written those answers in light. In the next part, we will turn from this big picture back to the theory itself. General relativity has passed every test we can throw at it, from Mercury to black holes to the expanding universe. Yet we know it cannot be the final word, because it collides with quantum mechanics at the extremes. To see where gravity might go next, we have to look at those cracks and the ongoing attempts to weld them into a deeper theory. Up to this point, general relativity has been the main character in our story. It tells you how space-time curves, how planets move, how black holes form, how the universe expands. It has passed every experimental test we have thrown at it. That might tempt you to declare the case closed. But there is another theory, just as successful in its own domain, that tells a very different story about reality: quantum mechanics. When you try to make these two giants share the same stage, they start arguing in ways that are not just confusing but logically impossible. Quantum mechanics rules the microscopic world. Electrons in atoms, photons in light beams, particles inside colliders, all obey its laws. In that world, particles behave like waves of probability. A particle can exist in a superposition of many possible states at once until it is measured. Outcomes are described by amplitudes that can interfere like ripples on a pond. This theory is unbelievably accurate. Every modern electronic device, from your phone to the computer running this video, depends on quantum rules being right. General relativity rules the macroscopic world. Planets, stars, galaxies, the expansion of the universe, all follow its geometric law, that mass and energy curve space-time, and that matter and light follow geodesics in that curved geometry. In this world, if you know the state of space-time and matter at one moment, the equations tell you exactly what happens next. There is no built-in randomness. The evolution is smooth, continuous, and deterministic. Most of the time, these two realms barely overlap. You do not need quantum mechanics to calculate the orbit of Jupiter. You do not need general relativity to understand how electrons move in a transistor. Each theory stays in its lane and works brilliantly. The trouble begins in places where gravity is very strong and things are very small at the same time. Inside a black hole, or in the first tiny fractions of a second after the Big Bang, you cannot ignore either theory. Space-time is extremely curved, and quantum fluctuations are huge. That is where the contradictions become impossible to avoid. Take the singularity at the center of a black hole, as predicted by general relativity. In the equations, curvature grows without bound, densities go to infinity, and the usual description of space-time fails. Physicists usually treat infinities like flashing warning lights that say the theory has been pushed outside its domain of validity. Quantum mechanics tells us that at incredibly small scales, nothing is perfectly smooth. Fields fluctuate. Geometry should too. The idea of a single point with infinite curvature may simply be the classical theory trying to describe a regime that really needs quantum rules. Or consider the very early universe. Wind the clock back using classical relativity, and everything shrinks to a point of zero size and infinite density at time zero. But at such extreme densities and temperatures, quantum effects must dominate. Virtual particles erupt everywhere. Fields jitter violently. Trying to describe that state without quantum gravity is like trying to describe chemistry while pretending electrons do not exist. You get some broad strokes right, but you miss the heart of what is going on. There is also a deep clash in how the two theories treat information. In quantum mechanics, the evolution of a closed system is reversible in principle. If you knew the exact quantum state at one time, you could, in theory, recover the past and predict the future perfectly. The wave function spreads and interferes, but it never loses information. Even when you include measurement, the underlying mathematics preserves a quantity called unitarity that guarantees the bookkeeping of information is never violated. Now drop a book, a star, or a cloud of gas into a black hole. From the outside, all you need to describe the black hole, at least in classical general relativity, are a few numbers. Mass, spin, perhaps charge. Every detail about what fell in seems erased. When you add Hawking radiation, the problem becomes sharper. Over immense time, the black hole slowly evaporates. If that radiation is completely random, as Hawking first argued, then the information about everything that ever fell in has simply vanished from the universe. That is forbidden in standard quantum mechanics. The black hole information paradox is not just a curiosity. It is a signal that the frameworks we are using cannot both be right in their current form. Then there is the question of what spacetime is made of at the deepest level. Quantum field theory. The quantum description of particles and forces other than gravity treats fields as fundamental. Particles are excitations of those fields. Space and time themselves are treated as a fixed, continuous background on which these fields live. General relativity flips that. Space-time is not a background. It is dynamic and responsive. It bends, ripples, and evolves along with the matter inside it. Trying to quantize gravity by simply putting a quantum field on a fixed space-time does not work. The math blows up at high energies in ways that cannot be patched easily. Physicists suspect that at the Planck scale, a fantastically tiny length around 10 to the power of minus 35 meters, space-time may not be smooth at all. It might be granular, like pixels in a picture, or woven out of tiny loops or strings. Below that scale, the idea of a definite distance or duration may simply not make sense. General relativity, which treats space-time as perfectly smooth and continuous, cannot handle this kind of discreteness. Quantum mechanics, which handles discreteness well, assumes a stage that does not respond in the way relativity demands. All of this points in the same direction. We need a theory that reduces to quantum mechanics in weak gravity and to general relativity in strong but smooth regimes, yet still behaves sensibly at enormous energies and tiny scales. A theory of quantum gravity. We do not have it yet. There are candidates, like string theory with its vibrating extended objects and extra dimensions, or loop quantum gravity with its quantized geometry, but none has earned the right to be called the final answer. They are promising sketches rather than finished portraits. In the meantime, researchers are getting creative about where to look for clues. Some experiments try to catch gravity acting on objects that are just large enough to be manipulated and just small enough to stay in quantum superpositions. Can you put a tiny mirror or a cloud of atoms into a state where it is in two places at once and still see its own gravitational field behave quantum mechanically? Does space-time itself become entangled with quantum objects? If so, that would be a direct hint that gravity has to be quantum at some level. Others search the sky for imprints of quantum gravity in ancient light. Primordial gravitational waves from the first instant after the Big Bang might carry signatures of whatever quantum process drove that era. Tiny deviations in how particles travel across cosmological distances could reveal a subtle graininess in spacetime. So far, every test has come back with a somewhat frustrating answer. General relativity still works. Quantum field theory still works. No obvious cracks. This is both humbling and exciting. Humbling because the universe is not obliged to reveal its deepest workings on demand. Exciting because we know there is a clash, and clashes are where progress happens. In the next part, we will look at some of the boldest proposals for resolving this standoff, from vibrating strings to holographic universes, and ask what they might mean for the future of physics and for our picture of gravity itself. When two of your best theories refuse to agree, you have a choice. You can pretend the conflict is just a detail and look away, or you can stare right at the crack and ask what reality is trying to tell you. Quantum mechanics and general relativity disagree in the most extreme places in the universe. That disagreement is not an embarrassment. It is a treasure map. Somewhere in that clash is a deeper description of gravity. We do not have that final description yet, but we do have some intriguing sketches of what it might look like. One of the oldest and most famous sketches is string theory. The idea sounds simple when you say it out loud. Maybe the fundamental building blocks of nature are not point particles, but tiny vibrating strings. Different patterns of vibration show up to us as different particles. One pattern looks like an electron. Another looks like a photon. Another looks like the hypothetical particle that would carry gravity in a quantum world, a graviton. In this picture, gravity is not added by hand. It is built into the menu of possible string vibrations. Strings do not like to live in a universe with only 3 dimensions of space and 1 of time. The mathematics naturally wants more room. Some versions need 10 dimensions in total, others 11. Where are those extra dimensions? In many models, they are curled up so small that you would never notice them in everyday life, like tiny loops attached to every point in space. The shape of those hidden dimensions would affect which vibrations are allowed, and therefore which particles exist. That is a wild idea. The properties of electrons in your body could depend on the geometry of tiny invisible directions at each point in space. String theory is attractive because it treats gravity and quantum mechanics in one unified language and avoids some of the infinities that plague naive attempts to quantize gravity. It hints that space-time itself might not be fundamental. Instead, it could emerge from deeper objects and symmetries in the theory. The downside is that it is hard to test. There are many possible ways the extra dimensions could be shaped, each giving a different set of effective particles and forces. At present, we do not know which, if any, describes our universe. A very different approach is called loop quantum gravity. Instead of replacing particles with strings, it goes directly after spacetime itself. In loop-based pictures, geometry is not continuous. It comes in discrete chunks. Areas and volumes are made of tiny indivisible units, woven together in a network of loops called a spin network. At large scales, that network looks like smooth spacetime. At extremely small scales, it looks more like a quantum fabric with a definite grain. In loop quantum gravity, the hope is that this discreteness tames the infinities of classical relativity. Curvature can grow very large, but not truly infinite, because there is a smallest meaningful size. The Big Bang might not be the absolute beginning, but a bounce where a previous contracting phase of the universe reversed into expansion when quantum geometry pushed back against further collapse. Inside black holes, the singularity might be replaced by an extremely dense but finite region where the spin network changes character. Like string theory, loop quantum gravity is elegant on paper and difficult in the lab. It makes some broad predictions, such as the existence of a minimum area. But tying those predictions to concrete observations is challenging. Neither framework has yet produced a clear, crisp signature that says, "Check this number and you will know we are right." Still, they are valuable because they show us something crucial. There is nothing sacred about space-time as a smooth background. In both pictures, geometry is a derived concept, not the starting point. Then there is the holographic idea, which sounds almost mystical at first encounter. It arises from studying black holes and the way their entropy behaves. Entropy is a measure of how many microscopic states a system can have. For ordinary objects, entropy tends to scale with volume. Double the size of a gas cloud, and you roughly double the number of ways its molecules can be arranged. Black holes break this rule. Their entropy scales with the area of the event horizon, not the volume inside. That area law suggests a wild possibility. Maybe the fundamental information about what is inside some region of space is encoded on its boundary, much like a two-dimensional hologram can encode a three-dimensional image. In certain carefully defined universes, physicists have shown that this is not just a metaphor. There is a precise mathematical equivalence between a theory with gravity in some bulk region and a different quantum theory without gravity living on the boundary. Every event in the interior has a counterpart in the lower dimensional boundary description. If something like this holographic principle applies, at least approximately, to our universe, then space-time and gravity might emerge from patterns of quantum information on some deeper structure. In that view, asking what curves space-time is a little like asking what curves the surface of a wave on the ocean. The surface is real, and its shape matters. But at a deeper level, it is the collective behavior of countless water molecules that truly defines it. Some researchers even argue that the fabric of space-time is stitched together by quantum entanglement, the same spooky connection that links particles in quantum experiments. Change the entanglement pattern and you literally change the geometry. These ideas are radical, and they are not all compatible with each other. String theory, loop quantum gravity, and holographic dualities are not three versions of the same thing. They are different attempts to answer the same set of puzzles. Guided by different intuitions about what is fundamental, it is entirely possible that the final theory will borrow pieces from several of them, or from something we have not invented yet. From your vantage point, it might be tempting to dismiss all of this as speculative and distant. After all, does it really matter whether space-time is made of strings, loops, or quantum bits when you still have to catch the bus in the morning? But there is a historical pattern worth noticing. When we chase deep theoretical questions about how the universe works, we often stumble into practical revolutions by accident. Quantum mechanics started as a way to explain weird spectral lines in heated gases. It ended up powering lasers, transistors, and the digital world. General relativity began as an attempt to tidy up gravity, and now sits inside every positioning satellite and navigation app. The effort to quantize gravity is not just an abstract game. It forces us to rethink what space, time, information, and even reality itself mean at the deepest level. It may eventually reveal entirely new ways to manipulate space-time, or at least to measure it with unimaginable precision. It will almost certainly reshape our picture of black holes, the early universe, and the ultimate limits on knowledge and communication. We are, right now, in the messy middle of that process. Our best ideas are incomplete and sometimes contradictory. Our experiments are just beginning to nibble at the edges of the relevant regimes. That is exactly what it looked like historically, right before other big leaps. In the next part, we will turn back toward you, in a matter, your everyday life, and the technology you interact with, and see how this strange, curved, quantum space-time you live in quietly shapes everything from your phone to your future dreams of exploring the stars. After all this talk about black holes and the fate of the universe, it is fair to ask a slightly selfish question. What does any of this mean for you, right now, living your normal human life? Gravity feels boringly familiar. You drop your keys, they fall. You stand up, you feel heavy. Yet woven into your day, often in ways you never notice, are technologies and choices that only work because we learn to treat gravity as geometry, and not just a mysterious pull. The weirdness of space-time is quietly inside your pocket. Start with something you probably use constantly, even if you wish you did not. Navigation. The global positioning system is a swarm of satellites orbiting Earth, each carrying extremely precise atomic clocks and broadcasting their timestamps. Your phone listens to several of those signals at once and triangulates its position from tiny differences in arrival time. That only works if the clocks in orbit stay in sync with clocks on the ground. But they do not. Not naturally. Time runs at a slightly different rate up there, where gravity is weaker and orbital speeds are high. According to general relativity, clocks higher in a gravitational field tick faster than clocks deeper down. According to special relativity, moving clocks tick slower than stationary ones. GPS satellites feel both effects. Their height makes their clocks run a little fast. Their speed makes them run a little slow. Add the two corrections together, and the net result is that their clocks would drift ahead of ground clocks by tens of microseconds per day if we did nothing. That does not sound like much, but a timing error of a few billionths of a second translates into position errors of many meters. Within hours, your maps would be useless. Engineers solve this by building relativity into the system. The satellite clocks are preset and continuously corrected so that in the curved, dynamic spacetime around Earth, they keep coordinated time with the rest of the network. Every time your phone tells you where you are, it is using Einstein. Atomic clocks have gotten so good that we can see gravitational time dilation over a height difference of less than a meter. Put one clock on the floor and one on a shelf. The one higher up, in slightly weaker gravity, ticks faster by a tiny but measurable amount. That means if you spend your whole life living on the top floor of a building, while your twin lives in the basement, you really will age a little faster, though the difference is so small that it only matters to people who build the clocks. Our planet is a machine that gently stretches and squeezes time with altitude, and we have instruments sensitive enough to watch that stretching happen. The search for gravitational waves also forced us to advance measurement technology in spectacular ways. To sense a change in length smaller than a proton over kilometers of vacuum, you need lasers of incredible stability, mirrors whose surfaces are polished with absurd precision, and vibration control that can ignore traffic, storms, and even distant ocean waves. The spin-off technologies from that effort spill into other fields. Better lasers for communication and sensing. Better coding techniques for high-quality optics. Better strategies for isolating delicate experiments from environmental noise. Chasing whispers in spacetime gave us new tools for everything, from materials science to timekeeping. Astronomy itself has become a kind of engineering with gravity. Gravitational lensing, which we talked about earlier as a beautiful confirmation of space-time curvature, is now a standard instrument. Astronomers use massive galaxy clusters as natural telescopes. When a very distant galaxy happens to sit behind one from our point of view, the foreground cluster bends and magnifies its light. That lets us see objects that would otherwise be too faint and small. Instead of complaining that gravity distorts the view, we have learned to treat the distortion as an extra lens. The universe builds us telescopes out of space-time. Closer to home, gravity shapes how we build and inhabit spacecraft. Astronauts in orbit are not floating because gravity has vanished. They are falling with the spacecraft along a curved geodesic. Everything inside is in the same state of freefall, so no one feels weight. As you already saw, freefall is the natural state in general relativity. Standing still on a floor is the weird one, because something is pushing on you. If we want long-term space habitats that are kinder to human bones and muscles than continuous weightlessness, we can use the equivalence principle in reverse. Spin a large structure so that the floor pushes on your feet with a steady acceleration, and your body will interpret that as gravity. Rotating space stations in science fiction are just practical applications of Einstein ideas. Then there is the dream that will not die, traveling to the stars. General relativity sets hard speed limits. Nothing carrying information can move faster than light through space-time. To get a human-scale spacecraft to even a modest fraction of that speed would require staggering amounts of energy. Even if you could build such a drive, time dilation would twist the experience. For travelers going very fast, time would pass more slowly aboard the ship than back on Earth. A round trip to a distant star could fit within a human lifetime for the crew, while decades or centuries pass for everyone they left behind. They would return as visitors from the future, cut off from the world they knew. Physicists have played with wild ideas that seem to dodge this limit. The most famous is a warp-style drive, where you contract space in front of a spacecraft and expand it behind. The ship would effectively ride a bubble of curved space-time, moving faster than light relative to distant objects without locally breaking the speed limit, because inside the bubble it would never outrun light in its immediate neighborhood. Clever. The catch is that all known versions of this idea require exotic matter with negative energy density, something we have never seen in the quantities required, and that may not be possible to create or control. The equations permit the trick. Nature may not permit the ingredients. Even if the stars remain painfully distant, understanding gravity does not doom us to a small future. It sharpens our sense of what is realistically within reach. The solar system itself is vast. There is enough room and material in its planets, moons, and asteroids to host civilizations far larger than anything on Earth. Orbital habitats, cities on Mars, mining outposts in the asteroid belt, floating communities in the skies of gas giants, all exist within a regime where our current understanding of gravity and propulsion is perfectly adequate. On those scales, general relativity is not an obstacle. It is the blueprint that tells you how fast you need to go to orbit, how to transfer between worlds with minimal fuel, and how to keep people healthy in artificial gravity. Gravity also plays a quieter but crucial role in planetary defense. Near-Earth asteroids follow geodesics determined by the combined curvature from the Sun, planets, and their own motion. A tiny nudge at the right time, perhaps from a kinetic impactor or a gravitational tug from a nearby spacecraft, can slide an asteroid onto a slightly different geodesic that misses Earth instead of hitting it. Because orbits are sensitive to early pushes, our ability to predict and alter these paths depends entirely on understanding gravity to high precision. Einstein equations are not just about distant galaxies. They sit under simulations that may one day decide whether a dangerous rock skims past us or does not. So when you think about gravity now, try not to reduce it to the feeling of heaviness in your legs. It is the hidden framework that keeps your navigation apps honest, that makes spaceflight possible, that sets the realistic boundaries on interstellar dreams, and that gives us a real chance of steering away cosmic hazards. It is also the thing that made stars, planets, and your own atoms in the first place. In the final part, we will pull all of these threads together, from falling apples to expanding space, from your heartbeat to the heat death of the universe. We will take one last long look at what it really means to live your whole life inside a curved, dynamic space-time, and why understanding that is one of the most human things you can do. Take a second and notice your own body. The pressure of the chair or bed under you, the weight in your feet if you are standing, the simple fact that things fall when you let them go. After everything we have talked about, you can now translate that everyday feeling into a very strange sentence. Right now, you are being pushed away from your natural path through a curved four-dimensional space-time. You are not being pulled down by gravity. You are being held up by electromagnetic forces in whatever you are resting on. That reframing sounds subtle, almost like word games. It is not. It is a complete flip in how you think about what is natural and what needs explaining. In the old picture, sitting still was normal and falling required a special force. In the relativistic picture, free fall is the simple default, the state where no force acts on you. Standing still on the surface of a planet is what needs an explanation, because something has to constantly push on you to keep you from following your own geodesic. Once that clicks, even ordinary experiences start to look different. Jump in your imagination. For the brief moment when your feet leave the ground, you are in genuine free fall. If you could somehow remove the floor and keep that motion going without air resistance, you would feel the same weightlessness that astronauts feel in orbit. Not because gravity turned off, but because you stopped resisting it. When you watch a ball arc through the air, you are literally watching an object trace out a geodesic in the curved space-time around Earth, only slightly disturbed by air. That is what reality is doing all the time. Zoom out in your mind from that jump to the orbit of the moon. Earth is doing the same thing around the Sunday. The sun follows a long geodesic around the center of the Milky Way. The galaxy falls through the larger scale curvature of the cosmic web. You, the chair you are sitting on, the planet, the star, the galaxy, All of it is moving through a dynamic geometry that none of us chose and all of us share. Understanding that does not magically solve your problems or pay your bills. What it can do is change the background story you tell yourself about what kind of universe you live in. This is not a place of arbitrary rules handed down from nowhere. It is a place where a few deep principles keep showing up in wildly different contexts. Mass and energy. Curve, space-time. Objects follow geodesics in that curved space-time. Those simple facts give you falling apples. There is something quietly reassuring about that unity. The same equations that describe the orbit of Mercury also describe the bending of light from distant galaxies and the ripples from colliding black holes. The same equivalence principle that tells you why astronauts float tells you how to fake gravity with a spinning space habitat. You do not live in a fragmented reality where each scale plays by unrelated rules. At the same time, the story is clearly unfinished. General relativity works stunningly well and yet fails when you push it all the way to singularities. Quantum mechanics works stunningly well and yet refuses to sit comfortably with curved space-time. Dark matter and dark energy dominate the universe, and we do not know what they are made of. The early universe and the deep interior of black holes are still blank regions on our conceptual map. We have equations that describe a huge range of phenomena. And then beyond those, big question marks. Those question marks are not a failure of science. They are exactly what scientific progress looks like from the inside. Once, people did not know why planets moved at all. Then Newton wrote down a set of laws that unified falling apples and orbiting moons. For centuries, his theories seemed complete, until tiny discrepancies like Mercury precession and the behavior of light near the sun hinted that something deeper was going on. Einstein followed those clues to general relativity. Now we are in a similar position. Gravity has been mapped in extraordinary detail, yet the edges of that map are frayed. Those frayed edges are invitations. You might never personally write down a new equation of quantum gravity, and that is fine. You are still part of the only known species that can even pose the question. A species that can detect a change in distance smaller than a proton over kilometers of vacuum. A species that can image the shadow of a black hole in another galaxy. A species that can look at faint microwave noise in the sky and read from it the age, content, and history of the universe. That capacity to understand is not an extra garnish on top of being alive. It is one of the most beautiful side effects of matter becoming complex enough to think. There is also a kind of ethical weight that comes with this view. It does not care what lives on them. Yet out of that indifferent process has emerged at least one pocket of the universe where atoms have assembled into beings who can feel, care, and choose. Learning the rules of space-time gives you power. How you use that power is up to you. You can aim it at building tools that help more minds flourish for longer, or you can aim it at short-term gains and hope someone else deals with the consequences. The universe is not taking sides, but your choices still matter to the small region of space-time you inhabit. Next time you look up at the night sky, you can see more than twinkling dots. You can see gravitational wells holding stars in their galactic orbits. You can see light that has spent millions or billions of years threading through the curved geometry between its source and your eyes. You can see the echo of a hot beginning imprinted in the darkness between stars. You can remember that the atoms in your body were once inside other stars, fell together under gravity into this planet, and now, for a brief time, are arranged into a pattern that can ask the question, what is gravity really? And you can carry one last thought. You are not separate from the space-time we have been talking about. You are a temporary pattern within it. Your heartbeat, your thoughts, your relationships, all unfold along a world line. A path through space-time that is just as real as the orbit of the moon or the trajectory of a comet. Understanding gravity is, in a quiet way, understanding the stage on which your own life happens. It does not make your experiences less meaningful. If anything, it makes them more astonishing. You are surfing the geometry of the cosmos from the moment you are born until the moment your world line ends. You do not get to choose the large-scale shape of that geometry or the cosmic era you were born into. or the ultimate fate of the universe. You do get to choose what you do with the tiny piece of space-time you occupy. You can ignore it and let the days pass as if they were obvious. Or you can look around, understand a little bit of how impossible it is that you are here at all, and let that awareness sharpen how you live. If you have followed the story this far, you have already done something very human. You have turned a simple everyday sensation, the feeling of weight, into a doorway that opens onto the entire universe. You have walked through that doorway. And now, when you drop a ball and watch it fall, you will know that you are not just seeing a force. You are seeing the shape of space-time revealed in motion.